All right, today we are diving deep into a piece of tech that's, well, it's quietly powering just about the entire AI revolution, from the chatbots you talk to the weirdly specific products that pop up in your feed. It's called a vector database, and it's the secret sauce that's teaching computers to understand one of the most human things there is: meaning. So it really all boils down to a question that seems simple, but is actually incredibly deep. I mean, think about it. For you and me, the link between king and queen is just obvious. But how on earth does a computer, a machine that just thinks in ones and zeros, get that connection? How can it possibly grasp context and nuance and all those fuzzy relationships? That is the exact puzzle we are going to solve today. For decades, our whole digital world has run on a keyword search. You type in fast red car, and it goes off looking for pages that have the literal words fast, red, and car. Simple enough. But what if the perfect article for you uses the phrase quick crimson automobile? Well, traditional keyword search is just going to miss it completely. This is where semantic search changes the game. See, it doesn't just look for words, it looks for meaning. It actually understands that fast and quick are related and that car and automobile are basically the same idea. And that is a fundamental shift. So here's our game plan for this journey. First, we'll see exactly why that old school keyword search is hitting a wall. Then we get to the fun part, the magic of how we can actually teach a computer what things mean. After that, we'll look at how all this meaning gets organized into this giant virtual map of data and why searching that map is a massive challenge. Finally, we'll meet the vector databases that solve that very problem and really unlock this whole AI-powered future. Okay, so let's start with the problem. For all their power, traditional search systems are just surprisingly literal. They're rigid. They just don't have the flexibility that human language has. They're fantastic at finding a needle in a haystack, but only if you can describe that needle perfectly, down to the last detail. And these failures, they run deep. Synonyms, like we just talked about, are a huge blind spot. Then you have words with multiple meanings. You search for bank, and a computer has no clue if you mean a riverbank or a place to get money. It just has zero context. And don't even think about asking complex questions. Keyword systems just completely choke on them. And this isn't just a text problem either. I mean, how do you use keywords to search for a feeling in a song or a particular style in a photo? You can't. It's impossible. Okay, so if keywords are the problem, what's the solution? Well, this is where it starts to get really cool. We need a way to get past the words themselves and into the world of ideas and concepts. And the technology that makes this happen is called vector embeddings. And honestly, it's not an exaggeration to say this is the bedrock of modern AI. So what in the world is a vector embedding? At its core, you can think of it like a translator. It takes any kind of data, a word, a picture, even a song, and it translates it into the universal language of math, specifically a long list of numbers called a vector. But here's the thing, these are not random numbers. This vector is like a rich numerical fingerprint that captures the true essence of the original data. It places it on a huge conceptual map, what engineers call a high-dimensional space with literally hundreds of different attributes. So how does this translation actually happen? Well, it happens with these enormous AI models, like the ones you see here. These models get trained by basically reading a huge chunk of the internet. Think all of Wikipedia, millions of books, countless articles. And by analyzing all that data, they start to learn the incredibly complex relationships between words and ideas. They learn that puppy usually shows up near words like dog, fluffy, and cute, and they encode all of those relationships into the numerical vectors they create. So, and this is the most important part, the vector isn't just some random ID tag. It's a location and a direction on that giant map of meaning. The vector for puppy is going to be located in the animal neighborhood, really close to dog and kitten, and its direction might point towards ideas like playful or young. This is how a computer stops seeing letters and starts understanding relationships. Now, this is where it really starts to feel like magic. This is the classic example that just blew everybody's minds when it was first discovered. If you take the number vector for king and you mathematically subtract the vector for man and then add the vector for woman, the resulting vector is unbelievably close to the vector for queen. Now, think about that. This proves the AI didn't just memorize definitions, it learned the abstract concepts of gender and royalty, just as a mathematical relationship. It's absolutely astonishing. So we've turned all of our data, our text, our images, our audio, into these really meaningful vectors. What we've actually done is create a map of meaning, a high-dimensional space where every single piece of data has a specific coordinate. And on this map, one simple rule applies: proximity equals similarity.
So how do we actually measure that proximity? Well, we use math. You might remember Euclidean distance from high school. It's just the straight line distance between 2 points. Cosine similarity is a little different. It measures the angle between two vectors. A good way to think of it is checking if two ideas are pointing in the same general direction. But in both cases, the rule is simple. The smaller the distance, or the smaller the angle, the more similar the two things are in terms of meaning. So a search for house cat is going to pull up a vector that's very, very close to one for kitten.
And this brings us to our next huge hurdle. It's one thing to have a map with a few thousand points. But what happens when your map has billions of data points, and each one is a complex vector with hundreds of dimensions? If you ask it to find the vector that's closest to your search query, checking every single point one by one, well, that would take forever. It's just not possible at that scale. So the solution can't just be clever. It has to be unbelievably fast. We need a way to search through billions of these data points in milliseconds. This right here, this is the exact engineering challenge that vector databases were invented to solve. The key innovation here is a family of algorithms called approximate nearest neighbor, or AN. And the most important word there is approximate. See, instead of guaranteeing the one single absolute closest point, AN algorithms promise to find points that are among the closest, and to do it thousands of times faster. It's a brilliant trade-off, really. For almost anything you'd want to do, a 99% perfect answer that you get instantly is way, way better than a 100% perfect answer that takes 5 minutes to show up. Now, one of the most popular ways to do this is an algorithm called HNSW, which stands for Hierarchical Navigable Small World. Honestly, the best way to think about it is like a highway system for your data. It organizes all the vectors into this multi-layered network. The top layer has these really long-distance connections, kind of like an interstate, while the bottom layers are packed with shorter connections, like local city streets. And here's how that highway system actually works. A search query comes in at the very top layer, and it uses those long-range interstate connections to immediately jump to the right general neighborhood on the map. Then, it drops down a layer, refining its search on the state highways. It just keeps going down, layer by layer, getting more and more precise on the local streets until it pinpoints the closest neighbors at the very bottom. This whole structure just makes navigating a ridiculously huge space incredibly efficient. Okay, so we have a way to turn data into meaningful vectors, and we have these super fast algorithms like HNSW to search through them. The last piece of the puzzle is putting all of that together into one single, optimized system, and that system is the vector database. You see, a vector database isn't just a place to store things. It's a complete, high-performance engine. It handles all the data, it uses these crazy fast indexing methods like ANN for retrieval, and it gives developers a query engine to easily search for meaning. It's the whole shebang, the entire toolkit for building applications on top of semantic data. And this isn't some far-off future tech. There's already a whole thriving ecosystem of these databases out there. You've got managed services like Pinecone that make it incredibly easy to get going without worrying about servers. Then you have these powerful open source options like Weaviate and Milvus that are built for massive industrial strength deployments. And there are even lighter options like Chroma, which are perfect for plugging right into your own apps. They all have their own strengths, but they're all solving that same core problem: fast, scalable search for meaning. So now we get to the payoff. We've gone through the tech, but so what? Why does this all matter? What does this new power to search by meaning instead of just by keywords actually unlock for us? And the answer is, well, pretty much everything. This tech is already reshaping the world all around you. In e-commerce, it's what powers recommendation engines that can find a shirt with the same vibe or style as a pair of shoes, something keywords could never, ever do. It's what lets search engines understand your complicated questions and just answer them directly. It's how you can search your photo library for pictures of my dog at the beach. And beyond that, it's being used in cybersecurity to spot weird patterns in network traffic, and even in drug discovery to find molecules that have similar chemical properties. I really love this way of thinking about it. If you think of a large language model as the reasoning brain of an AI, then vector databases are its long-term memory. They provide the context, the knowledge, the grounding in real-world data that lets an AI give you answers that are actually relevant and accurate. Without that memory, an AI is just a powerful machine for matching patterns, but it has no real connection to reality. And that really brings us to the final thought. For the first time ever, we have a way to search and analyze all of our collective knowledge, not by the specific words we use, but by the actual ideas they represent. We've basically built a library that understands the meaning of its own books. So the question isn't really how we search anymore. It's what we will search for. What new discoveries, what new connections, what new answers are just sitting there waiting to be found. That is the truly exciting frontier that this technology has opened for every single one of us.